Hi guys, welcome to topic 2, communication. In this particular topic, we're going to be talking about a number of network and internet related topics. We'll talk about how networks work, network topologies, cloud computing, transmission media, meaning, for example, copper wires, fiber optic, how data is actually transmitted, LAN hardware, so hardware involved in networks, the internet, IP addresses, and then some other random hardware related topics. We're going to start with network fundamentals, which is going to go over a fair number of topics that are related to the types of networks that we use and how they're structured. Now, to start out, what is a computer network? So basically, a computer network is a collection of interconnected devices that communicate and share resources with each other. Now, if you're watching this on Wi-Fi, then you are connected to a computer network that is connected to the internet. And also, if there are other computers connected to that Wi-Fi network that you're connected to, potentially you could share information with them. Now, there are a few functions of computer networks. One is data sharing. Another is resource sharing. So data sharing basically just means sharing files, applications, and data. Resource sharing means we might be able to share peripherals or storage devices. So this is like when your school network, where you can use printers through your school network. And when anyone on the network can use those same printers. With storage devices, we're talking about hard drives that might be connected to a network. So just an external hard drive that's connected to a network that anyone who connects to a network can use. We can also use networks for communication. Now, this is more when we're getting into the topic of the internet. The internet is technically a network. So through the internet, we can do things like send emails, messaging, and video conferencing. And finally, computer networks allow for collaboration. This can either just be in a network where we're sharing files and sharing resources, or this could be through the internet, which again is a network where we're using actual web applications in our browser to work with each other. Now, there's some kind of fundamental components of computer networks, regardless of whether they're the internet or they're your home wireless network, that are present. The first is something called a node. And this is basically the device that you use to access a computer network. So this could be something like a computer, a server, which is really just a computer, a smartphone, or a printer. So any device that's connected to a computer network is a node. So besides nodes, we also need to have transmission media. So transmission media are basically what connects the computers to each other. Now these could be things like Ethernet cables, fiber optic cables, or any like wired transmission media, so wires just generally, or we could also use wireless signals to connect different nodes or different devices on a network. So some examples of that are Wi-Fi or just radio waves, or microwave transmission or satellite transmission, which we'll talk about later. The point is you need some way to transmit data between devices on a network. Now finally, we need devices that allow us to communicate on a network that basically resolve and organize communication between different devices on a network. And some examples of such devices are routers, which you've probably heard of, and which this is a router, switches, hubs, and modems, which basically allow you to connect to the internet in most cases. Now we're going to talk a bit about some of these networking devices, and this is just kind of an introduction to them because we're going to go into these in more detail later on. Now the first I want to talk about is a router. So basically what a router does is it connects different networks together. Like that's one function. But also what it does is it tells data where to travel in a network. So we're going to have a router in a network, and that router may receive data from one computer, for example, this computer. And the router, actually I guess this is technically a switch, but that router, which would go through the switch, to right here, or that data which would go through the switch to right here, would actually figure out where the data needs to go and then send it to its intended destination, which I guess could be back to this client or could be somewhere else. So the point is that a router accepts data from different clients, different nodes in a network, regardless of where they are, and then sends it to the right destination. And a router also allows us to connect different networks, like for example right here, this router is connecting the internet, LAN 1 sales department, and LAN 2 accounts department. Now again, there are many other functions of routers that we'll get into in more detail in a later section, But what you need to know is that routers are essential to sending data between networks and between devices on those networks. Now, the next networking device we have is a switch. Now, switches connect multiple devices on the same network. Routers generally allow us to connect different networks together, but switches, which we see right here, allow us to connect different devices on the same network together. And basically what they do is they allow us to send data between devices on the same network. So again, I just want to compare and contrast this with a router just to make it really clear what the differences are. But like, for example, here, a router allowed us to send data between different networks or even back to the same network, and also connected us to the internet, which was a network by itself. And it kind of rerouted communication between all those networks. Switches are working within a specific network. So if you're on your home Wi-Fi network and you want to send information to someone else on the network, you're probably going to be going through a switch. And oftentimes things like this, which you probably have one of these in your house. It kind of doubles as connecting to the internet, but also giving you Wi-Fi. Like, this says router, but oftentimes these devices will contain a router, will contain a switch, and will contain a hub that kind of have multiple devices within them. So this may not just be a router, but it might also have, for example, a switch inside to facilitate not only communication with the internet, but also within the network itself, so that we can share information within the network. And you may not physically send files to other computers in the network, but probably something you have done is actually streamed video from your computer to your TV, and those are both nodes on your network, and that's being done through some kind of switch functionality usually, unless you're just streaming it through the internet. But generally, if you were just streaming on your network, which is kind of how it works a lot of the time, then you're probably using a switch. Now, there are actually some terms here that I didn't really talk about, and one of them is data packets. One thing you do need to know is that whenever you're transmitting information on a network or between networks, it's going to be in the form of a data packet. So let's say that, for example, you want to send a message from this computer right here, from computer 1 to computer 2, through the switch. And let's say that's an image. Basically, that image, which is a fairly substantial amount of data, is going to be broken up into a bunch of different pieces. And each one of these pieces will become a data packet. And those data packets will be individually sent from one computer to another computer. And on each data packet, there's information like the destination computer, the IP address of the destination computer, in what order they should be transmitted and then put back together, etc. So each data packet has information that kind of guides it through a network, which the router which either the router and the switch or both will read to send it to the correct destination. And it also contains the data that we want to send. Another term you probably may run into is called a MAC address. And basically what a MAC address is it's an address that every network device has that's been stamped on it in a factory. So each one of these computers has some sort of device to connect to a network where you'd plug in an Ethernet port or that you'd use to connect to Wi-Fi. Each one of those devices has an address that's been imprinted on it in a factory. And oftentimes this can be used in order to kind of figure out where to send packets and allow us to basically organize data transmission between or across networks. So you've covered routers, you've covered switches, with the main distinction between routers and switches being that switches are working within a network and routers are actually connecting different networks together. But hubs are an even simpler device that honestly probably aren't used that often. Like with switches, we can just send data from one computer to another. So we just send it through the switch, and then that forwards it to a destination computer on the network. But a hub works a little differently. So if we send data from one computer, it sends it to every single other computer on the network. So it doesn't just send it to the destination, but it sends it to all computers that are connected. And this could be useful, but also you're kind of generating a lot of network traffic that you don't really need. And it's really up to the destination computers to decide whether to accept data sent by one computer or not. One of the advantages and one of the reasons that hubs may be used is because they're cheaper and simpler to configure than switches. So if you have a really complex network, there may be situations where you want to use a hub. But in general, I would say that you're more likely to run into things like switches and routers, particularly when you're dealing with questions on the A-level exam, but then also in real life. Now, the next concept we're going to talk about is called a local area network. Now, as you can see, this represents a local area network. You have a bunch of different devices that are connected to a switch, and this switch might be connected to other local area networks via a router. But at the moment, this just encompasses our local area network. So there's some things you should know about a local area network. What it is really just a computer network, but it covers a small geographic area like a building or campus, maybe a school campus, and honestly probably even smaller than that. And it basically allows all the devices connected to the computer or connected to the network to communicate with each other. Now, a great example of a local area network is your Wi-Fi network. Like, that is a local area network. Now, the primary reason we use local area networks are, again, to share resources like files, printers. Maybe you could use it for gaming. Basically, just to allow computers on the network to communicate with each other. Like I said, oftentimes a local area network will be connected to a router to allow it to access the internet. And all the computers on the local area network can make requests to and from the internet via the router. Now, the next thing I want to point out is that it's usually a pretty fast way of connecting devices together. We're going to have high-speed connectivity, usually through Ethernet, which is just a cord, or Wi-Fi. So this is an A-level question. Give two characteristics of a LAN. And one is covers a small geographic area. And two, which I actually didn't mention, is that the infrastructure is privately owned. It's not controlled by an external organization. I think this is kind of just alluding to the fact that a lot of local area networks are basically like someone's Wi-Fi network at a house, or they're at a business. They don't necessarily need to be privately owned, but generally, if something is owned by the government, it's going to be much, much larger than a local area network. Instead, it's going to be something called a WAN, or a wide area network, which we'll get into later. The next A-level question, give two benefits of connecting computers to a LAN. So we'll talk a little bit more about this later, but two advantages are that we can share files and data. We can allow the sharing of resources like hardware and software applications, which is, I guess we could share hardware. This is an example of that would be like having a hard drive connected to a local area network that everyone could access. Software, maybe an example of software would be like gaming software where we can connect to each other using a local area network. But a local area network also allows for centralized management, so we can manage security. We can back up all the data on a network or on the devices on a network, etc., through a local area network. I'd probably say these are probably the two easiest to remember. Next, explain how data is transmitted between two laptops in the LAN. So if you really want to talk about how we would transmit data is sent from the sending laptop is transmitted to a router or a switch. The data has the address of the recipient. And really we're talking about like data packets. And if you remember earlier when we talked about data packets, each data packet contains one piece of data and it has the destination of that piece of data. And all the data packets are sent one by one or sent in some order to the destination, put back together, and we basically have our data at the destination. Anyways, the data has the address of the recipient. The router determines the recipient's destination address by using a routing table, and the router transmits data directly / only to recipient. So that's how data can be transmitted between the two laptops in the local area network. Although you could also replace router with a switch, and that would still work. Now, this is just another example of a local area network. Here we actually have a router instead of a switch. But a router can also just be used to transmit traffic in a network. And again, connect one local area network to other local area networks. Now, the next type of network we're going to look at is a wide area network. And to be honest, this is like pretty much the same as a local area network, except that the geographic size is much larger. So we could have a wide area network that spans cities, like a citywide network, countries, or even continents. Actually, the internet's an example of a wide area network. This allows long-distance communication and resource sharing between different locations of an organization or between different organizations. It's basically meant for efficient data exchange over vast distances. Now, usually like with a local area network, we're going to use like Ethernet cords or Wi-Fi, but we're going to need something a little bit more heavy duty for wide area networks. We might use leased lines, which are basically huge, like just huge cables that are used for that are only used for a specific purpose, like this wide area network, a satellite communications, or cellular networks. So the point is, we're going to need some pretty heavy duty equipment to connect different devices in a wide area network, partly because a wide area network spans a huge area, but also because we're going to have a lot more devices by its very nature. And we're going to have different devices, like a huge number of routers to go along with that. So this is a great example of a wide area network. This is basically a connection of different local area networks. We only have 4 here, but there are probably going to be others. And we have different routers or other network devices to facilitate the communication. These local area networks may be spread across a city or some other large geographic area. Okay, so here we have another example of a wide area network. In this case, the wide area network is the internet. And the internet is actually kind of linking up with other wide area networks and other local area networks. So right here, for example, we have a city, which would probably be a WAN, and then we have a government or a set of government institutions, which could be a LAN and WAN. These are kind of connected to each other through using the same internet service provider, which does technically put them on the same network, which this ISP, like, it's going to be a set of network devices connecting them, and altogether they would probably form like another wide area network that's connected to a larger wide area network, which is the internet. Here we have a university campus. This is probably going to be a LAN, and an enterprise should probably be a LAN again. But these are connected to an internet service provider along with a bunch of other devices that are connected to the greater, larger wide area network, which is the internet. So you've kind of got a combination of wide area networks and local area networks that are connected to each other through one larger wide area network, which is just the internet. Now that brings us to our next slide, which is comparing both of them. So as we said before, local area networks, smaller area like a building or campus, wide area network, larger geographic areas like cities, countries, or continents. Local area networks are going to use switches, hubs, and routers, which are also going to be used in wide area networks, but we're going to have some devices that allow us to link up the network over larger geographic areas and that allow us to handle more data flow, like leased lines, which are just larger like cables, satellite links, modems, and routers, which again are going to be around. LANs will typically use things like Ethernet cables, fiber optic, and Wi-Fi, versus again, we're going to have things like satellite links, cellular links, and leased lines, which are just really large cables that are dedicated to network transmission, as well as more heavy-duty fiber optic cables. And with local area networks are primarily focused on internal communication and resource sharing. So think about just an office building. There we just really want to be able to communicate with each other and over the internet, and maybe share resources between those computers in that particular office building. Versus the wide area network, we want some more long-distance communication and resource sharing between different local area networks or networks. So a great example of a wide area network might be a military network that's used by a military with a global or large geographic presence, like the US military. And they might have communications links. They might have a wide area network that allows them to share data between installations in the United States and other bases that are located globally. We've got an IB question, or sorry, an A-level question right here. Identify 2 differences between a WAN and a LAN and larger geographic area. Right here it says line connections between devices are usually physical versus WAN connections are often virtual. That doesn't really make sense to me. I don't really actually know what that means. But here it does say that a LAN is a high data transfer rate and a WAN has a low data transfer rate, which actually does tend to make sense because of the fact that with the WAN, typically if we're transmitting data over longer distances, that means that it's going to just be slower. Things like satellite communication are often slower, and cable, like the signal that's going across a cable, is often going to be weaker over longer distances, which means we're going to have a lower data transfer rate. We have another point here that says that ownership of a LAN is private, while ownership of a WAN can be private or public. I mean, probably, yeah, a LAN is usually going to be private. We're not going to have a publicly owned local area network because there's no reason the government would get involved with something that small. And here also, the LAN is usually more secure than a WAN because protection is easier to implement. So with a local area network, it's just easier. We have like a smaller number of computers, and we have all our network infrastructure is within a smaller area, so it's easier to secure it. Versus a WAN, we're trying to protect a global network with a huge number of devices, so it's just going to be a lot more difficult. Next, state whether the network will be a local area network or a wide area network. Justify your choice. A school is setting up a network within one of its buildings, and if it's just like a building, I think it's pretty obvious it's going to be a local area network, small geographic area, and we don't need any like external infrastructure. We don't need to lease any external infrastructure. And we're not using the internet to transmit within the building because the internet would make it a wide area network. So we might use the internet inside a building, but we don't necessarily need to. Now, the next thing we're going to talk about is network models, or like how we can model the interactions between computers in a network. And the first model we're going to talk about is going to be the client-server model. So the client-server model is probably what you're used to. This is when a device interacts with a centralized server. And a server is just a computer, but this is like a really great analogy for how our interactions with the internet works. So for example, if we want to access like facebook.com, really what we're doing over the internet is we're sending a request to some central server at facebook.com that is sending as a response. So you have devices that act as clients that ask for information and that will maybe send information. And all of that those requests for information and the destinations of the information will be a central server located somewhere else that will respond and react accordingly. So if we were to formalize some typical characteristics of a client-server model, client devices like computers, smartphones, etc. request and receive services or resources from a centralized server. Clients are typically user devices, and servers are powerful machines that host, manage, and provide resources such as files, applications, and databases. And the communication in the client-server model happens over a network using certain protocols that allow us to kind of formally initiate requests for information or data and receive responses. And this protocol also allows for efficient resource sharing and management. Now, some common use cases for the client-server model are going to be web services. So this is when we're in our web browser and we're accessing information. We want to get information from a website. Email services, so sending and receiving emails, and file sharing. So if we're kind of, I guess, sending files to and from different, or maybe if we're uploading files to a server on our network that allows other people, from which other people can download files, or even if we're on the internet and we're uploading files to some like storage site and people can download those files from that storage site. Now, as with all models or all paradigms, there are some pros and cons to the client-server model. So some of the pros are centralized management. So everything is kind of, you just need to really manage that server that holds all the data or resources that we're trying to access. Data consistency. This means that all clients can access the same data from the server. So different clients aren't going to see different data. Everyone has access to the same data. And security. We really just need to be able to enforce security policies and manage user access to one centralized server, which makes it more secure. We don't really care about the clients that much as long as that server is secure. On the other hand, we have a few cons. The first is a single point of failure. So if the server goes down, really nothing works. We really need that server to be up. And this leads us to our next point, which is dependence on that central server. So not only do we not have a single point of failure, but all clients are dependent on that central server. So even if that server doesn't go down, but there's some problems with it, then we're going to run into issues. Additionally, servers can become overloaded. So if you have too many clients trying to access the server at the same time, it can become overloaded, and basically any tasks will become slow. So accessing information or accessing data or resources on that server will either be problematic, it won't happen, or it'll just be really slow. This stands in contrast to our next model, our next network paradigm, which is the peer-to-peer model. Now, peer-to-peer networks stand in contrast to client-server networks, and the fact that there's no centralized server. So if this was a like client-server network, then you'd have one centralized server right here, and all of these would connect to it. But it's not, so we don't have that. Instead, every node, so every computer in a peer-to-peer network is connected to every other computer. So right here, we have, for example, this one. This is connected to this computer right here, this computer right here, this computer right here. And yeah, actually it's connected to all of them. So basically you can think of it as everyone being connected to everyone else. Every peer is connected to every other peer. Now these connections may not be constant, but basically every computer can access every other computer on the network to a certain extent through some software program or whatnot. And this is just another comparison right here between what a client-server network would look like and what a peer-to-peer network would look like. So just some basic facts about a peer-to-peer network. It's a decentralized network where each device has equal status and can act as both a client and server. So if you go back right here, this computer can hold data. So for example, this computer right here could hold data that other computers in the network want, and it could simultaneously or not simultaneously access data from other computers. So every computer can both serve other computers and access or receive services from other computers. Versus right here, we only have one larger computer that is going to dispense services, and we have all the other computers are just going to access it. They're not going to give the server or act as a resource for this main server right here. So peers share resources directly with each other without the need for a central server, distributing the workload and resources among the connected devices. And they communicate directly over the network rather than through a server. So if we, in a client server model, any communication, so if client 1 wanted to communicate with client 2, it would have to go through the centralized server. But right here, if client 1 wanted to communicate with client 2, that could happen directly. I guess it's not client 1 and client 2, but just node 1 and node 2. But I think it just makes it easier to understand. In many cases, this can be more efficient and create for more scalable resource sharing. Now, some of the common use cases are file sharing. If you've ever used something like BitTorrent or uTorrent or something like that to download movies off the internet, then that is an example of a peer-to-peer network. Communication services like Skype, for example, that allow direct communication between users without relying on a central server are peer-to-peer. Also, things like cryptocurrencies and blockchains are examples of peer-to-peer communication because we have transactions through a blockchain network without peers. So there's no centralized server, but every transaction between different peers or different computers on the network is recorded in a blockchain, which makes sure that the transaction between them is valid. So we have an A-level question here. Describe the key features of a peer-to-peer network. And here, all computers have equal status. Each computer provides access to resources, and data is distributed. Computers can communicate and share resources. Each computer is responsible for its own security. And this is an important distinction because really with the client-server model, the server we just really need to secure the server, and clients were kind of on their own. Here, each computer, so the clients, I guess the clients were responsible for their own security as well. But here it's kind of different because every computer is being accessed by every other computer, right? Like really in a client-server network, the clients weren't accessing each other. They were only accessing the central server. So we didn't really have to worry too much about security in a client-server model, but here we do because every computer can access every other computer. So again, some of the pros and cons of a peer-to-peer network are we'll start with the pros. So some of the pros are the decentralization. It's because there's no central server. If one computer on the network goes down, the rest of the network can still function. Also scalability. So we don't really need to worry about server overload like we did with the client-server model. We can have as many computers in the network as possible all join up and transmit data with each other. Cost efficiency is another pro of peer-to-peer networks because we don't need to maintain and secure a central server. Everyone just kind of joins up on their own, and they're responsible for the cost of their own device. Finally, privacy. So there's no central server that's like keeping track of our communication and our basic interactions with other computers in the network. So the only computers in the network that have a record of communications or transactions is is our own computer and the one we're communicating with. So we tend to have greater privacy in a peer-to-peer network. However, there are some cons. It's hard to manage security and enforce security policies across all computers. So we don't really necessarily know who we're communicating with on a peer-to-peer network. And really, we just need to focus on securing a central server in the client-server model versus, and I mean, if we're only focusing on securing that central server, we have a lot of control over security. We have pretty consistent policies. But here it's kind of a free-for-all, so security can be hit or miss. Data consistency is challenging because data is located on different computers. So with the client-server model, we're all reading the same data. So we're all looking at the same files, the same data, versus on a peer-to-peer model, we could, for example, have a file that's called, I don't know, Breaking Bad on one computer. We could have another file called Breaking Bad on another computer, but they could be different because there's no real consistency. Like, again, it's kind of a free-for-all. We don't have a single server that we can manage and where we can make sure that all data is like organized and is easy to distinguish. Finally, performance variability is another factor. So different computers will dispense data or dispense resources at different rates because they'll have different internet service providers, and network connections. So the quality and the speed at which we can access different peers on our network that we can access and we can get access to data on our network is going to vary a lot. Versus with a server, that server has the same internet service provider. And we're still going to have some variability in terms of like how fast we can access data, but it's never going to be a question of as to how fast data can be accessed from the server, like how fast the server can communicate with us. It may be fast, it may be slow, but it's going to be consistent. Versus with peers with a bunch of different computers, we don't really know what we're going to get. That brings us to our next concept, which is thick client and thin client architecture. So the best way to think of thick client and thin client are, well, these are both client server models, but in the thick client, our computer is more powerful and doing most of the work. And in our thin client, our computer, which we're using, is less powerful, and the server is doing more of the work. So it's basically like how we're sharing the workload. I think probably a great example would be a banking application. Well, not even a banking application. Let's think of an application that does data analysis, something like Excel. In a thin client, maybe our computer is using a desktop version of Excel. So most of the analysis is happening on our desktop, and we're simply storing data. Well, I guess that would actually be a thick client. But in a thick client, we have Excel on our computer and our like a desktop version, and most of the data analysis is being done using our computer's resources, and we're simply storing data on a database server. In a thin client, we might just be accessing Excel through a web browser. So we're just really running the web browser on our computer, and the actual analysis, the kind of heavy duty stuff like crunching numbers, is being done on a remote server somewhere. That would be a thin client architecture. So thick client, more work on your computer on the client side. Thin client, more work on the server side. This is just another way to describe it. So the thick client, really a lot of the interaction and response is happening to the software program on a computer. And we have a thick client and a thin server. So you might just have some really basic, like just getting some data from a thin server. The thin client, we're doing more interaction, receiving more responses from a thick server. And so I would actually say that most applications nowadays, especially like mobile apps, are going to follow the thin client paradigm, because it's really just like, okay, we're just using our app to really just pull data off a server somewhere else. And most of their like heavy lifting is being done on some remote server somewhere else. Now with a thin client, I think, so basically with a thin client, we're relying on a central server for processing power, storage, and application management. And our client, the device we're using, is going to be minimal. So that's going to be our smartphone, tablet, or even just a weak computer. Again, with a thick client, so most of the processing tasks are done locally on our own computer, on our own device. and things like processing power, storage, and application management. That's mainly happening on our own device, not on a server somewhere. And we can run applications independently, store data locally, and with the thick client, even if we lose our internet connection or network connectivity to some central server, we're still good to go because we're doing most of the work on our own device, our own client device anyways. So if we wanted to like compare both of them, in terms of processing power, we could say that the thin client would have low processing power and relies more on the server, versus a thick client would have high processing power and would do most of it locally. Similarly, a thin client's going to have minimal local storage, while a thick client's going to have high local storage capacity. So by local storage means storage on your own computer, the one you're using to actually interact with, and that's on your side. With a thin client, we really need to have network connectivity. So in most cases, we need to always be connected to the internet. Think about something like Google Docs or even Google Sheets. It's only really done through like a web browser. And with the thick client, we don't necessarily need the internet. So think about something like Microsoft Word or Microsoft Excel in sort of the pre-internet days where we could just do a bunch of stuff on our own computer. Now, because of that, a thin client is going to be easier and cheaper because like we don't really need to do much. We don't need to pay more for a more powerful processor or more storage space or more RAM. Versus a thick client is going to be more complex and costly because we're going to have more of those resources. Also, updates and management are just kind of done from the server, versus with the thick client, we need to actually update our software on our own. So it's just going to take more time and be more complex and costly. So now let's move on to our next topic, which is network topologies. And this is basically the structure of a network. Now, more specifically, it refers to the arrangement of various elements of the network. So basically like how different computers are connected to each other on the network, and also like where network devices are located, with network devices, of course, being like switches, routers, computers, and other peripherals. Now, network topology is important because it affects how efficient the network is in terms of data transfer and resource allocation. It affects the scalability because some networks or some network structures allow us to more easily add other nodes or other devices to the network than others. It affects fault tolerance because the network structure can affect how easily a network can continue to function when one or more devices on the network or nodes have failed. And finally, network topology affects the cost. Certain layouts or certain structures of networks require more cables and more hardware devices than others. Now, the first network topology we're going to talk about is bus topology. In basic bus topology, we have like one main cable, and each node communicates off this cable. So we just have one main cable that acts as sort of a conduit for all communications in a network. Now, this single central cable is called a bus, which makes it a bus topology. And because it's a fairly simple structure, which means its setup is simple and inexpensive, but the network is quite vulnerable to failure. Because if, for example, this cable gets cut at any point, then the network is pretty much going to stop functioning and certain nodes will be disconnected from other nodes. Now, the way that bus topology works is data is broadcast to all devices. So each device checks if it is the intended recipient, leading to a potential data collision or leading to potential data collisions or retransmissions. So basically, like I kind of talked about how communication works, but not really so much in depth. Basically, what happens is when data is broadcast to the bus, that's basically sent to every single node, and then the node decides whether it's going to accept it or not. And if the node wants to communicate that data, that's being sent to also every single other node on the bus. And this can often create some problems. So we can have data colliding with each other. So for example, if one node is transmitting while another signal comes through the bus, those could collide with each other. And we might also have to like retransmit data as a result. Now, if we want to talk about the scalability and performance of a network that follows bus topology, we could say that adding more devices increases collision likelihood. And again, by collision, we're talking about the collision of signals. And it's because of the fact that every single signal is going to be broadcast, like every single signal that's sent either on the bus or from a node is going to be broadcast to every other node on that particular network. And so this can lead to different signals like sort of colliding with each other if they're being broadcast at the same time, because there's just a lot of signals being sent to every single node at the same time, or like any time you want to send anything. And this is why bus topology is less suitable for large networks. So if you have a network with a few devices, it can work because we can kind of resolve these different pieces of data, these different signals that are being sent across the network quite easily. Also, there's not really going to be that much network traffic, so it's not really a big deal. But if you have a larger network, this may not be for us. We mainly use bus topology because it's cost effective. We don't need much cabling, mainly just the bus and devices and cable to connect devices to the bus. It's pretty simple to set up, and it's ideal for temporary networks. So because of the sort of simple configuration, if we have a network we need to set up really quickly, then it can be something that's ideal. So something we're setting up out in the wild somewhere, or if we just have an event, we need to set something up, then bus topology can be quite useful because of how simple the structure is. And the next type of topology I want to talk about is star topology. So star topology is basically a topology where devices are all surrounding a hub, or it could even be a switch. Right here it says hub, but that's not necessarily always the case. The point is we have things arranged like a star with one central sort of device that's allowing communication between them. So basically, whether it's a hub or a switch, that can affect how effective it is, but this can actually be useful in terms of how fault tolerant the network is, because if there's ever a problem with the network, we know where the problem is going to be. It's going to be at this central hub or switch, because it's kind of the only point that facilitates communication. But at the same time, that can make it more weak or more like susceptible to problems, because if that fails, then the network stops working. Basically, the pattern in which data or signals are sent across this network is to the central hub. So data from any device is sent to the central hub or switch, then routes it to the destination device. And this means that we're not going to have different transmissions colliding with each other, different signals colliding with each other, because we basically just send a device and just goes to another device. And we kind of have a hub or switch regulating when signals are broadcast, when they're sent, kind of doing a bit of traffic control here. And again, like a lot of the information I think I found was really referring to the fact that it's a switch, that we have a switch in the center, because a hub actually does just send the same signal out to every device. So I think it's probably better just think about star topology in the context of as not necessarily having a hub in the center, but probably just more likely having a switch. In terms of scalability, so adding or removing devices is really simple because you just want to hook them up to that central device. So we can say that star topology is highly scalable while still maintaining good performance. And what's also important to note is that we can just add another device, and that device is not going to affect any of the other devices on the network. So generally, we use star topology when we want a network that has easily troubleshooting and maintenance, when we just don't want to have to spend a lot of time troubleshooting a network. We want scalable networks, and when we want low collision risk, basically we want a strong management of data traffic when we have quite a few devices on the network. So we have an A-level question here. One of the company's offices has one server and 4 computers connected in a star topology. Draw a diagram to show the layout of the office's star topology. In this case, probably the server is also going to function as a network device, it's going to have a router or some sort of network connectivity or network function as part of that server. So we can see right here, we have the server in the center, and we have each computer connected to that server on its own. They're not connected to each other, just all of them are each individually connected to the server. I don't know why I just said that so slowly. I guess I was trying to emphasize it. Anyways, that's basically a star topology in the context of the A-level exam. Now, another question. The LAN is set up as a star topology. Draw a diagram of the topology of the LAN. Now, we don't really have much context here, but this is just another example of a network. So right here, presumably we have servers. We have a server on the network, but we also have 2 laptops, and we have a router. So in this case, I guess we can assume that the server is not a network device since we have a router. But that router is going to be in the center, and every device in the network is going to be connected directly to that router. Yet another A-level example. A local area network consists of 4 computers, 1 server, and a switch. The LAN uses a star topology. Complete the following diagram to show how the hardware is connected. Now, this is sort of like a weird diagram right here. So basically, I don't know why it's like sort of drawn this way, but I think it's pretty safe to assume that our switch is going to be the network device, and these 4 computers right here and the 1 server are all going to be just clients on the network. They're going to be other devices in the network. So basically the answer is all 4 computers are directly connected to the switch and know their connections. It doesn't really say anything about the server, but I would assume that the server is also connected to the switch as well. Like it doesn't really give much detail into this, which is kind of weird, but basically every device is going to be connected to that network device. So every computer, of which a server is usually just a computer, is going to be connected to that network device. And again, so Andy plays some computer games over the internet. He has several devices that connect wirelessly to the router in his house. This is actually just more of a real-world example. Identify the topology of Andy's home network and justify your choice. So this is like a home Wi-Fi setup, and generally in this case, each device is just going to be connected to the router. Hence, it's going to be star topology. But we'll kind of look at the justification. It says, of course, star topology, devices are connected directly to the router independently, and they're only connected to the router. So they're not connected to each other necessarily. They're not directly connected to each other. If they communicate, it's done through the router. Now, the next type of network we have is a mesh network. And this actually resembles a peer-to-peer network. In fact, I think a peer-to-peer networks basically follow the mesh topology. And it's basically where every computer in a network is connected to every other computer in a network. So we have interconnected devices, which means that we have multiple paths for data transmission. But I think one thing that's important to point out that we could distinguish from just peer-to-peer networks is the fact that, well, I guess this is actually true in peer-to-peer networks as well to a certain extent. But basically every node can communicate with every other node through other nodes. So node 1, for example, could communicate with node 3 this way. But if for some reason this connection was severed, then it could also communicate through node 2 to get to node 3. And that makes these highly durable to nodes just disappearing. It just makes them very fault tolerant. So basically data can take several possible paths to reach its destination, so that if one path is gone, there's still other paths to reach a destination. And as a result, these are highly scalable. So we can add a bunch of different devices, and we don't need to worry about having communication pathways just because of the way they're set up. I mean, we do need to connect them to the network, but the idea is that there's going to be, if we're working in an environment where the network is susceptible to disruption, we can still operate a huge number of devices, and we can quite easily add new devices and allow that network to still work robustly. We can also handle high traffic volume efficiently because there's just multiple paths through which data can travel. One downside, though, is that mesh networks can be complex and expensive to set up because of the extensive cabling and hardware required. So more cabling, more connections means potentially, just first of all, more wire, which is expensive, potentially more hardware devices or network devices. So a network uses 5 different topologies in different areas of sites. In one building, there are 5 computers connected in a mesh topology. Describe what is meant by a mesh topology. So all computers are connected to at least one device. There are multiple routes between devices, and computers connect as relays, passing packets, data packets, which you talked about earlier, on towards their final destination. Now, why do we use mesh topology? They're highly reliable, and they have lots of redundancy. And by redundancy, this means there are multiple ways to accomplish the same task to get to the same destination. So they ensure network availability, even if one path fails. Moreover, because we have so many pathways, we can handle high data volumes quite efficiently. Finally, mesh topology, kind of because the above 2 points are very fault tolerant. So if parts of a network disappear, we still have ways to access all the devices in our network or to send data from one device to another throughout our network. And this can be especially useful for data centers or in military communications, which are environments that do have a lot of possible disruptors to a network. Now, identify 2 advantages of using a mesh topology over a bus topology. Again, this is an A-level question. So our answer here is that if one line goes down, there's no more routes available, and this is true in a bus topology. Versus in a mesh topology, we have multiple ways to communicate with any of our devices. So if one communications link goes down, we still got plenty others. Also with mesh topology, we have improved security because we are not just using one line. So for example, if someone's trying to hack our network, or if they want to tap into our network, they can access all the data by just tapping into the one bus, the one line in a bus topology network. That's not necessarily true in a mesh topology network where there could be multiple routes that data is taking. So data could be taking one of many different routes. Fewer collisions because of multiple routes to transmit data. Also, new nodes can be added without interruption or interfering with other nodes. I mean, I guess this is kind of true for bus topology as well, but potentially, I guess if we're connecting to a bus, it could create some problems. But mesh nodes are just known for being more scalable in general. More secure because data is sent over a dedicated connection. So this kind of goes back to just the reason why mesh networks are better at security than bus networks. We have the potential for a dedicated connection between two devices. So if you go right back here, again, we do have different routes, but also we do have, like, for example, the idea is that we'd have dedicated connections between two devices. So we're not always necessarily going to be passing through other devices in order to get there. So that is some security in and of itself. So we have a few different answers. This one is maybe a bit suspect because I think that they're both fairly scalable, but the others all make quite a bit of sense. And we really only needed two from these. Now, the last type of topology that we're going to talk about, topology, not typology, is actually hybrid topologies. And this isn't like a single topology, but just the idea that we can use multiple different topologies in the same network. So right here we have different star. We got star, star, star. And here we have something called a ring topology, which is actually something we didn't really need to know for the A-level exam. But it's basically where computers are connected in a ring and other computers on that network are utilizing a star topology. So that's an example of a hybrid topology. It's just a combination of multiple topologies. This gives us more flexibility and scalability because we can kind of combine different topologies based on what are the specific needs of our network. And we can also get improved performance and reliability because, again, certain parts of our network might require more reliability than others. And we can account for this by, for example, using a mesh network in one part of our network, or just using a bus topology in another part of our network. So we can get the adequate or the appropriate amount of fault tolerance and efficient data transmission that we need for our particular use case. And that brings us to our next topic, which is cloud computing. Now, cloud computing is basic technology that allows users to access and use computing resources such as servers, storage, databases, networking, software, and analytics over the internet. So a cloud computing tool is usually something we can access over the internet from our web browser. So a great example of cloud computing would be anything in the Google platform, like Google Drive, Google Docs, Google Sheets. All of that is cloud computing. But oftentimes things get more complex, especially when we host full web applications on cloud computing platforms. But anyways, to kind of just bring it back down to probably the simplest possible terms, it's just technology that allows us to access computing resources over the internet. Now we've got two types of public clouds, or we've got two types of clouds, and the first cloud is a public cloud. So by a cloud, we're talking about a cloud computing service provided by a company. So this is a set of tools that we can use through our web browser to store data, to process data, to do any number of things. And we can divide these cloud computing services into two types, public and private, as I kind of mentioned before. A public cloud is a service that can be accessed over the public internet. So again, the Google platform, Amazon Web Services, all that is stuff that can be accessed over the public internet. So those are all examples of public clouds. So some key characteristics of public clouds are accessibility. These are they're services that are accessible to the general public. Like if you wanted to upload an application to the Amazon Web Service and host it from there, and also make use of any AI resources, any number of resources. That's something that you just as an individual can do. Also, public cloud services, users can easily scale resources up or down based on demand and pay only for what they use, which provides for flexibility and cost efficiency. And these cloud services, these public cloud services, are managed by providers. So usually something like Amazon, Google, DigitalOcean is a big player, or really any public or any company that's providing this to the public. They're going to be responsible for managing not only just the functionality of the system, but also things like security, taking care of infrastructure, and just general user experience. And the whole point of clouds is that users can make use of resources that are somewhere on a server somewhere else so that they don't actually need to manage physical hardware. And I think I probably should have pointed that out in the beginning. We use cloud computing so that we don't actually have to deal with physical hardware ourselves, buy that hardware, and just kind of manage it. So the students can save their school files in a public cloud. Identify 2 drawbacks of the students storing their files on the public cloud. So first, if students were to store their files in a public cloud, they can't access their files without a reliable internet connection, which is what we alluded to before. We're basically accessing a public cloud service through a web browser, which means it's over the internet. And the amount of space for no payment may be limited. I mean, in a lot of cases, a certain amount of resources might be free, but at some point you're going to have to pay for what you use. And students do not have control over the backup or security of their work. So oftentimes, pretty much any time you use a cloud-based service, you're not really in control of it, which means you're also not in control of things like security. So there is the possibility that your work could be stolen or tampered with in some way if security is not taken very seriously on the end of that cloud service. Now that brings us to the next type of cloud, which is a private cloud. And this is a type of cloud computing that is dedicated to a single organization. So this is still cloud infrastructure that we would need to access over the internet, but it's something that is solely for a single private organization like a company. And this allows for enhanced control and privacy over data and applications, because those resources that you access over cloud computing are not being shared with any other individuals or any other organization. It's purely just for your company. So you tend to have more control, and just your data and your infrastructure isn't being exposed to other users. And generally with private clouds, you also, because you're the only organization using that cloud environment or cloud service, you're often given the opportunity to customize your cloud environment. And oftentimes this is done to meet certain regulatory requirements or compliance in a certain country for things like privacy, which goes along with enhanced security. Usually with private clouds, because you have more control over your infrastructure and your data storage and any of the resources you're using. And because you can enforce things to a greater extent, like security and compliance, generally things are going to be more secure for you. So we have an A-level question that just kind of talks about the concepts of clouds in general. But right here it says the diagram shows the hardware and software used to retrieve files stored in the cloud. So you've got a laptop, you've got a firewall, and through that laptop, we're accessing our cloud through our internet service provider. So we've got A. So the name of the device A that allows the laptop to connect to the internet, a type of cloud X, and an example of an application B that can run on the cloud. So this is presumably some kind of application that's running on the cloud. Complete the following table by writing the answer for each row. So the name of the device A that allows the laptop to connect to the internet is most likely a router, I guess. The type of cloud. So if just anyone can go ahead and access this right here, it's probably going to be a public cloud. And an example of an application that can run on the cloud. I guess there's a whole lot of examples. I guess you could just say any like web-based application. I'd be curious to see what the mark scheme says though, because it's not really that specific. So let's see. So yeah, the name of the device A that allows the laptop to connect to the internet is a router. This is a public cloud. Here we have a variety of different examples of applications that could be run on the public cloud. Email, graphics, word processor, spreadsheet, pretty much anything. I guess the best way to approach questions like this would be to think of them through the lens of something like Google Drive or the Google suite of tools, so like Google Docs, Google Sheets, anything like that. Now, we talked about private and public computing, or cloud computing, and what cloud computing is in general. But what I'd like to talk about is some of the advantages of cloud computing. And the first is scalability. So because you're not having to physically, like, if, for example, if you want to add more storage, or if you want to make use of more storage in a web application or any service that you're using, if you were kind of doing it on your own without cloud computing, you'd have to physically go out and buy a hard drive and then stick into your computer. But with cloud computing, you can just scale up resources based on demand. So you don't even have to, you don't have to have any resources or any storage or any processing power that's not being used. You can set your service to automatically scale the resources for your application up or down based on how much they're being used, which allows you to spend as little as possible. You only pay for the resources used, and again, resources might be processing power, memory, storage space for any application you're hosting or you're making use of in a cloud-based system, but you're only paying for what you use. Also with cloud computing, you can access data and applications from anywhere on the internet, from anywhere with an internet connection rather, facilitating remote work and collaboration. You really just need an internet connection to access your cloud computing service and any applications that are a part or hosted in that service. And finally, reliability. So if you are just using applications in your own computer, you're really just dependent on your internet connection and the stability of your immediate area. Generally, cloud computing services are very, very large, and they're set up to prevent any disruption to that service in general, because if a cloud computing service is not working, then they lose money. Their whole job is to just sit there in a data center and allow people to access them whenever they need to. So you're going to have minimal downtime and probably more data protection than if you weren't using cloud computing. Now, that being said, there are some disadvantages of cloud computing as well. First is security concerns. So we talked about this earlier. You really just don't have, so that the data or the resources in cloud computing are going to be in a data center somewhere, which is just like a massive complex with just a bunch of computers really. And because you don't have control over the company and over the company that runs the service and the service itself, you don't really have any control over how they handle security and things like data privacy. So there could be some security concerns. Also, there are risks of downtime. So depending on where that data center or where that cloud computing service is based, where its resources are based, there might be some instability, there might be a lack of internet connectivity. Obviously it's probably going to be better than your home system, or your home, just using your home computer, but that's also a risk. And third is this limited control. You just don't really have control over the infrastructure and software, and particularly if the company that you're working through, so if your cloud provider gets bought out by another company or something like that, or takes on new management, you don't really have any control over what happens to your data or your applications or anything that you have stored within those resources. And finally, with cloud computing, compliance can be a challenge because of the fact that the actual resources that are enabling that cloud service could be located in different countries or different locations. And depending on what country you're in, the regulations can kind of be different. So just kind of the dispersed international nature of cloud computing can lead to compliance challenges. Okay, so the next section we're going to cover is going to be on transmission media. And transmission media is basically representing the physical media through which data and signals on a network are transferred, so through which they travel. We have a few types of media we're going to look at. First of all, we're going to talk about the difference between wired and wireless networks. We're also going to look at fiber optic, cable, radio waves, Wi-Fi, microwave, satellite transmission, etc. So let's get started. Now, the first thing I want to talk about is wired networks. So wired networks are basically when we just have wires connecting different computers on a network. And there's some advantages to this. It tends to be quite fast. So wires can transmit data more quickly than wireless networks, which use radio waves. Less time waiting, fewer delays, it's more reliable. Also with wired connections, you don't have to worry about walls or other objects being in between your wireless access point or between computers that are connected on a wireless network. And it's also more secure, largely because if you want to tap into a wired network, you pretty much physically need to connect to that wired network, which is much more difficult than just kind of like hiding somewhere and connecting to a wireless network. Also, oftentimes with wired or wireless networks, we can have issues with things like interference, with other networks interfering with each other, or with networks interfering with each other, which is not really as much of a problem with wired networks. But some of the disadvantages of wired networks are the fact that we do need physical cables, which can be expensive and difficult to work with, especially to install and manage. Also, we have limited mobility for connected devices. So because every device on a wired network has to be connected via wire, we can't really move it around as much. Also, maintenance costs tend to be higher just because, again, we have an actual physical wire. Now, next, we're going to talk a little bit about wireless networks. So wireless networks are probably something you're already pretty familiar with. So it's basically when we have networks where computers are communicating with each other using radio waves, and you're basically accessing a wireless access point or a router that is sending radio waves to your computer, which you are then emitting back to that particular wireless access point. There are obviously some advantages of this, which is mobility and convenience. You can kind of just walk around and sit anywhere within range of a wireless access point and get access to Wi-Fi, get access to that network. Installation is easy, it's scalable. We can easily add new devices to the network. It can be cost effective for large areas. We don't need to spend money on cables. So it's cheaper than trying to connect all the devices in a large area to an access point or to a network. And this is because there is reduced physical infrastructure. However, oftentimes wireless networks are slower, meaning higher latency. So it's going to take more time to transmit data. The connection can be less stable, especially when there are other wireless networks around, which can lead to interference. There's security risks. It's easier to tap into a wireless network because you don't necessarily physically need to be connected to some network device or some aspect of the network. You can kind of just be anywhere within range of a wireless access point, and you can go ahead and just connect to that network. So it's a lot easier to kind of hide and tap into a wireless network than with a physical network. And there's a limited range, which is like kind of true for wired networks as well. But with wired networks, your range is really only limited by how much cable you're willing to use to connect computers. So we have an A-level question here. Melinda mainly uses the internet to watch films and play games. Tick one box to identify whether Melinda should connect to the router using a wired or wireless network and justify your choice. So she's going to watch films and play computer games. So basically what we need to do is, right here it's asking us to identify whether she should connect to the router using a wired or wireless network. So we need to pick one of these and then justify it. And there's one mark for each justification. So for wired networks, some justifications might be faster connection, more reliable, and more secure. And for wireless networks, freedom of movement, easily expanded, so it's easy for people to connect, less cabling / expertise is needed, which means setup is less expensive. Another A-level question, students can connect their devices to the university network using cables or a wireless connection. Explain the benefits to the students of allowing them to use both wired and wireless connections. It's not just wired, but also both wired and wireless connections. So there are some benefits to kind of having what we could call a hybrid network in terms of transmission media. So some students might only have one sort of connection on their device, although I guess this kind of shows how this exam is kind of dated sometimes. Like everyone has access to a wireless network now on their laptop. But wired could provide better performance for the students' devices. There would be less interference if students could connect via cable. And having the cabled option could also be great for security, so they can transmit work more securely. However, wireless connections mean that students can freely use their devices. They can roam around and use them in different rooms or different areas. Also, they can easily connect up multiple devices or switch devices when needed to. So if you have if you have the option to connect using both a wire and wireless connection, then you have access to all the advantages of both media. Okay, so now that we've talked broadly about the two types of networks that we would be working with, wired and wireless networks, we can actually talk about the media or the actual material that makes up the connections between devices in these networks. Or in the case of wireless networks, the types of radio waves or electromagnetic frequencies that allow us to work with networks or to connect different devices networks. Now, the first transmission media is going to be copper cables. This is something that everyone should be familiar with. This is probably the most common transmission media in your house, even just for electricity. Now, copper cables have some advantages. They are quite cheap. They're easy to install and manage. They're reliable, and they're not as susceptible to interference. They're also quite secure, just in the sense that they're difficult to kind of tap and to kind of eavesdrop on without someone else knowing, partly because they're just a physical media. The disadvantages are they have a limited bandwidth. So using copper cable to transmit data, it's going to allow you to transmit less data than with fiber optic for any given amount of time. They're susceptible to electromagnetic interference. So I guess think about putting like a magnet against or next to a copper wire or something like that. They're heavier and bulkier than fiber optic. And we'll talk about what fiber optic is in a second. So fiber optic is basically wires made of glass through which data is transmitted. But generally, copper cables are quite heavy and bulky. They have a shorter lifespan due to oxidation. Copper oxidizes, which means that we're going to have to swap out copper cables every certain amount of years. So they are more secure maybe than like Wi-Fi, than a wireless transmission media, but they can still be tapped easily. I think tapping phones is like a pretty well-known thing. And we have reduced signal intensity over distance. So the longer the cable is, the less intense the signal is going to be by the time it gets to the end of a cable from the other end of the cable. And this can often be a problem when we're trying to transmit data over long distances. Now we can kind of evaluate copper cables in comparison to fiber optic cables. And fiber optic cables are basically cables that are made up of glass or plastic, and data is transmitted as beeping light signals. Not beeping, but basically we transmit data as light through the cable. So light is going to be shined through a glass or plastic shard or fiber, I guess, and it's just going to be turned on and off like extremely frequently. We're talking about 1,000, actually probably even more than that, times a second in order to transmit bits of data. But in a lot of ways, it is superior to copper cables. So it has a high bandwidth and speed. There's a low loss of signal strength over long distances, where it's immune to electromagnetic interference. So there's no electromagnetic waves that can really interfere, or spectrum that can interfere with copper cables. It's lightweight and thin, and it has higher security. So it's much more difficult to tap a fiber optic cable than a copper cable, partly because if you do tap it, then it's probably going to be pretty obvious to the sender that it's being tapped, because you would be messing with the lights, with that light signal. However, anything can really be tapped. It's just more difficult with fiber optic cable. The disadvantages are that it's more expensive, both to just the cable itself and the installation. A specialized requirement is required for splicing and termination. So actually cutting the cord and connecting the cord to equipment. So just kind of like cutting the cord off can be quite expensive. There's less flexibility for bending. So if we do want to install fiber optic cable in a in a building that requires us to bend that cable quite a lot, then that can be a problem. And there's limited availability in some areas, so fiber optic is not something that is readily available everywhere. So just getting access to it in certain areas, perhaps certain countries, can be more difficult. I probably didn't explain splicing and termination correctly, but what you just need to know in that respect is that it's more difficult and expensive to install. So if we end up comparing the two, fiber optic allows us to transmit at a higher bandwidth, transmit data at a higher speed. It's immune to electromagnetic interference. It's lighter and thinner than copper cables. It's higher security, but it's more expensive. However, it is better for long distances. So really, like the main distinction between both of those, if you're trying to decide whether to install fiber optic or copper cables, is probably going to be things like security, cost, the amount of speed or bandwidth you need, and how, I guess, like the distance over which you would be transmitting your data. Now, next we're going to talk about Wi-Fi. This is something that I think everyone is aware of, and in this section, we don't need to delve too deeply into what Wi-Fi actually is. But it's basically a wireless networking technology, and we use radio waves to provide internet access, but also in order to allow computers to connect to a network. It's commonly used in homes, businesses, and public spaces, and allows mobility and convenience for connected devices. Basically, all those advantages we talked about of wireless networks. However, it is not the only way by which to transmit data wirelessly. The next way we're going to talk about is going to be using microwaves or microwave transmission. And basically, when we transmit over microwaves, like microwaves transmit data over line of sight, and it's going to be between these two dish-looking things, right? Of which there's a transmitter on one end and a receiver on the other end. And so we might send our data up into this microwave dish, send it over the airwaves, and then receive it at another microwave dish, and then connect it up to a computer to analyze whatever data we received or to be able to interpret it. Now, microwaves have a number of advantages. They are high bandwidth. They're capable of long distance communication. We don't need physical cables. They can be deployed quite quickly. They're less affected by physical obstructions than, let's say, like Wi-Fi. But they're also suitable for remote and difficult terrain. But they're susceptible to weather conditions like rain and fog. They require a line of sight between transmitters, which kind of actually puts this in question right here as to how they're less affected by physical obstructions. Maybe this is just something that's not really worth mentioning as an advantage because they require line of sight. There's a potential for signal interference. There's a high initial setup cost, limited flexibility in network expansion. Because like in Wi-Fi, you just need to broadcast Wi-Fi from an access point, and then computers can connect to it. With microwaves, you actually do need a transmitter and a receiver. And partly because they're line of sight, you require careful alignment and maintenance. So I'd probably disregard this. They do require line of sight between transmitters. Now, the next type of wireless data transmission we have to work with is satellite transmission. And if you've heard of Starlink, which has been in the news quite often recently, then you've heard of satellite transmission. Starlink is a type of satellite transmission. Now, there's some advantages. The first is global coverage, although this kind of depends on what areas a satellite's covering. Like initially, Starlink didn't cover the whole globe, and I actually still don't think it covers the whole globe. Also, sometimes satellite transmission is turned off in certain areas, for example, the occupied territories of Ukraine. But it is ideal for remote and rural areas because you are basically just accessing a satellite. Like you're receiving a signal from a satellite, and you're basically sending and receiving data in order to be able to get network access, to access the internet or whatever it is. It can provide you connectivity to mobile users, on ships, planes, etc. It's reliable communication in disaster situations precisely because you don't need to really rely on any physical infrastructure in order to, any ground-based infrastructure, besides maybe a receiver unit like this in order to be able to access the satellite. It supports a wide range of applications, TV, internet, GPS, although if we're talking about just networks in general, then we're mainly going to be talking about internet really, because if we're connecting to a satellite, it's not going to be to just access some network that is not connected to the internet, some sort of weird local network. Although perhaps if it's a military-based network, then it might be used to access that. You can also deploy satellite transmission quickly over large areas, particularly if the satellites are already in place. For example, Starlink receivers can just be plugged into a car, like a cigarette lighter, or just any simple electrical socket. There are some disadvantages to satellite transmission. So satellite transmission it has a high latency due to a long signal travel distance, so it's generally going to be slower than some sort of wired connection or a Wi-Fi connection. It's very expensive to launch and maintain satellites. You need a pretty substantial satellite network to achieve global coverage. It can be susceptible to weather conditions, so you're basically accessing a signal from space. So if there's something between you and the satellite, like rain or clouds, then that can degrade your data transmission capability. There's limited bandwidth compared to terrestrial networks, terrestrial being on the ground. So you're just going to have limited bandwidth compared to a mobile internet network, for example. We already talked about signal interference and degradation, although there could be signal interference from ground-based sources. It could be any electromagnetic interference, for example, GPS jamming or something like that. And there is the ability to jam the signal. And oftentimes you need specialized ground equipment, although I guess the Starlink receivers are still quite specialized. So generally satellite transmission can be quite high cost, and it doesn't have a lot of bandwidth. It doesn't give you a lot of bandwidth, but there are certain situations where satellite transmission is pretty much the only answer to being able to access the internet or networks. So we have an A-level question, give one advantage and two disadvantages of transmitting data using satellites instead of copper cables. So one advantage of using satellites is they're not fixed to a single location, and they allow access in remote and rural areas. But some disadvantages are high latency, lag, slow to connect, how much they cost, bad weather affecting the signal, and just a slower transmission speed. Also, you do need, this is something I didn't mention, but you do need a line of sight. So if you have, like, for example, with Starlink right here, you do have this like little receiver, and you have like a little sort of satellite dish that needs to be pointing upwards at the sky so that it can receive a satellite signal that's broadcasting down to it. Now our next section is going to be on the actual hardware that's used to allow a network to function, that kind of glues different computers together and takes the cables from computers and kind of puts them together in a certain configuration. And we've touched on a lot of these devices in some of the prior sections, but we haven't really gone into much depth as to what they are. So the first device we're going to talk about is a server. And servers are essentially computers. They are computers that are dedicated to supplying resources, data, or services to other computers, client computers over a network. And servers basically they're just computers really that become servers when they run a computer program that allows them to interact with the network, and as well if they have the hardware that allows them to interact with the network. They can host websites, manage emails, store files, and run applications. And when we're talking about the internet and accessing websites, websites are generally going to be hosted on a server, and our computer that we use to access those websites through a web browser are going to be the client computers. And the next device that we did talk about earlier is a switch. And this essentially connects multiple devices within the same network. And it directs data packets from one computer or data from one computer to another computer that is also connected to that same switch within the network. The next device we're going to talk about is a network interface card. Now, this is something that maybe you haven't really thought about in a long time, particularly if you're more used to using things like tablets. But these are hardware components that allow computers to connect to a network. And if we look at this right here, this is something that would be on a desktop, and it would be connected to the motherboard, and using an Ethernet cable, we would connect the computer to the network. Now, also we have wireless network interface cards, and it's basically the same concept. It's something that would be connected to the motherboard, but allows us to connect to a network wirelessly. And these are perhaps less common. Just because like most of the wireless enabled devices that we use today are things like laptops and tablets, and those have an internal NIC, or an internal wireless network interface card. So you're not really going to see these antennae, but they are something that can be used and something that can be connected up to a desktop computer or even a laptop to allow for wireless capability. And again, these are probably more commonly seen like 10 years ago. So A-level question, each laptop has a wireless network interface card. Describe the functions of a wireless network interface card. So they're pretty much actually what you would expect. Provide interface to a wireless network. They can also be used as an antenna. They receive analog radio waves and convert them to a binary signal. They check incoming transmissions for correct MAC IP address and ignore transmissions not intended for it. They can take part in encrypting or decrypting data, and this one we actually already saw. So ultimately they allow us to connect to a wireless network, but these are also some of the other capabilities that they bring to the table. One network in the building has 30 computers. The computer needs to be connected to the network. Each computer has a network interface card. Identify two possible devices that can be used to physically connect the 30 computers to the rest of the network. So router, switch, or hub. They all have the capability to connect to a network, but we do need these devices in order to allow all 30 computers to be on the same network and to communicate with each other. All of these would fulfill that. Obviously, a hub is going to be less efficient because it's going to broadcast the same signal from each computer to every other computer on the network. Probably a router and switch would be preferable, but we just need some two devices. Now, the next type of device we're going to talk about is going to be a wireless access point. And we kind of referred to this a lot in previous slides. I didn't really explain it fully, probably because I think it's something that everyone kind of knows. It's basically that thing that you connect to get Wi-Fi. So a wireless access point is responsible for creating wireless local area networks by connecting to wired networks and projecting Wi-Fi signals. So basically, with a wireless access point, it's also going to be a router, and it's going to be connected to the internet, and it's going to allow computers that are connected to a wireless local area network to interact with the internet to send and receive data from the internet. And it basically allows for consistent coverage in large areas. And anytime you go to a coffee shop, or even if you're at home and you want to connect to the internet wirelessly, you're going to be connecting to a wireless access point. Again, it's basically a router that is melded with some wireless capability to allow you to connect to it wirelessly. And the next type of device we're going to talk about that we haven't really talked about before is a bridge. So a bridge is basically something that connects different parts of a network, helping them work together. It links two or more network segments, allowing devices on these segments to communicate as if they were on the same network. By network segments, we really mean two different parts of a network, so two different groups of computers that are connected together. Basically, if we have two networks and we want to connect them, then we could use a bridge to do that. It helps manage data flow by checking the destination of data packets and deciding whether to forward or block them. So it's basically like a kind of a traffic control mechanism between two or more parts of a network, or two or more networks, different networks, I would say, that we want to put together so that they can communicate as if they were on the same network. Common types of bridges are transparent bridges, which allow us to connect different Ethernet networks, and wireless bridges, which allow us to connect wired networks but wirelessly. So I guess a transparent bridge is kind of the same thing, but we're just using a wire to connect different networks. With a wireless bridge, we're connecting different wired networks, but we're doing that wirelessly. So here's an example of a bridge. We have one network, and these are all connected together by a hub. And we have another network, and these are connected together by another hub, and they can communicate with each other through a bridge. So we've got an A-level question. Complete the following table by writing the purpose of each of these other hardware devices used to support the local area network. We have switch, wireless access point, and bridge. So switch allows two or more devices to communicate with one another, and allows us to receive transmissions and forward them to their destination. So basically allows communication between two devices. A wireless access point allows the connection of devices using Wi-Fi. It allows a central device to send and receive radio signals. That's a wireless access point. Allows wireless-enabled devices to connect to a wireless network. A bridge can connect two local area networks or segments. Segments are just parts of a network, but also we can just say that it allows us to connect two local area networks with the same protocol. And we can also transmit data between two networks with the same protocol. To be honest, I don't understand why the same protocol is necessarily emphasized. I don't think they'd be able to communicate unless they were communicating through the same data transmission protocol, but that is something that we should probably take into account when we are describing what a bridge is. Now, the next device that we're going to talk about is going to be something called a repeater. And a repeater is probably a simpler concept than a bridge or any of the other network devices that we've looked at. So basically what it does is it's used to extend the range of a network by amplifying and retransmitting signals. So let's say, for example, right here, let's say we have a router right here. I don't know why it shows a computer. And that router, or that wireless, we can say it's a wireless access point rather, has a certain range. But we want to increase that range. So somewhere between our target range and our actual range, we're going to put a repeater, so that a repeater can then take this signal right here and then amplify it. So basically make it stronger so that we can reach whatever our target range is. So basically it takes a weaker corrupted signal from one segment of a network, amplifies it, and retransmits it at a stronger and clearer level. And again, we could be talking like similar to with bridges. We could be talking about a network segment, which is just a part of a network, or we could be talking about two networks that we're trying to connect together. But it doesn't really matter. The point is a repeater is used to just extend the reach of a network. Interestingly, right here, it says it's used in both wired and wireless networks. I don't really see cases of it being used in wired networks that often, but I guess it's possible because if you have a wired connection between computers, the longer that cable is, the weaker the signal is going to be. So I guess it's still possible. Now, the next device we're going to talk about is arguably the most important device in terms of the A-level exam, and that is the router. Now, the router has a huge number of functions, but I would say like one of the primary functions of a router is to connect two networks and to help in the transmission of packets between those networks and between the devices on those networks. It basically acts as sort of a traffic cop, but maybe more than a traffic cop. It acts as probably like a traffic controller, a digital traffic controller in the context of a city. So it basically routes things where they need to go. So if we have a router right here, we might have some computers connected to a switch. That switch is connected to the router, and that router serves as kind of an interface to the internet, allowing us to send data back and forth to and from the internet. And the reason for that is because right here we have one network, and the internet itself is a big network, and the router is acting as sort of an intermediary between those two right there. So what I kind of wanted to do in order to illustrate how a router works is follow some data through a network and through a router to illustrate the different roles that a router plays. So when you send an email from your computer, that data is broken up into packets. We talked about data packets earlier, and these packets are sent to the router, which also receives packets from the internet and other devices in your office. So as we saw before in our previous example, the router is acting as both a traffic controller and intermediary between those two networks. Now, the router examines each packet's IP address to determine its destination. So that every data packet that comes together to make up that email, those packets are sent to the router, and the router looks at the IP address for where those data packets are to be sent. In another example, if you're accessing a website, the router checks the IP address of the website to know where to send your request. So from your browser, if you are sending a request, you want to see google.com, that request is going to take the form of data packets, and the router is going to send those to the IP address of google.com in order to be able to get the actual website that's associated, the actual HTML web page associated with that website. And the next step kind of illustrates that. After identifying the destination, the router forwards the packets to their intended location. If you're accessing a website, the router sends the request packets to the website server. The server responds. The router ensures that the response packets are delivered back to your computer. So the router is not only facilitating you sending a request to the website or sending data packets of an email to whatever email service you're using, but also when that website or when a server responds, or even when another computer on a network responds, the data packets that make up that response are delivered back to your computer via the router. Now, another thing that the router actually does is it assigns IP addresses. So if you've ever I don't know if you've ever messed with your router's settings before. Obviously I don't know because there's a bunch of people watching this, but if you ever messed with your router's settings, you might notice that each computer that's connected to your router has an IP address that looks something like this. It's like 192.168.01 or some variation of that, something like that. So basically each device in your office network gets a unique private IP address in the router. And this private IP address is only visible to anyone else in the network and to your router. And that's just something the router does, and that ensures that the data sent and received within the network reaches the correct device. It's sort of like a private phone book for inside your network, and that's created by the router. So perhaps that's not necessarily associated with the previous three steps you looked at, but just another thing the router does that you should be aware of. Now, another role of the router is the router maintains a routing table. So it basically keeps a table of, it basically allows the router to effectively direct packets to their destinations by the most optimal paths. So it's basically keeping a table of all the different devices in your network, as well as routes to get to those devices. So it's basically allowing you to most efficiently send packets to their destination. And so as I pretty much just said, like having a routing table is kind of the way or the method by which the most efficient path is found, and like network speed is optimized to be as quick as possible. So basically we can transmit data as quickly as possible to our network and to the router and to its intended destination. So we have a routing table, and that's basically keeping track of what devices are on the network and routes between devices. So different routes data can take. So a router will also keep track of, as we kind of said, not only the IP addresses on the network, but also MAC addresses. And we talked about this earlier. These are addresses that are sort of inalienable parts of any network-enabled device. And it's just an address that's stamped on a piece of hardware in the factory. The router also gives your entire network a single public IP address. So you might have a router that you connect to on your home computer, and you've got a couple of computers that connect to it, like so. These are my horrible drawings of computers and a router. But when the internet, like so, when you connect to the internet, any other server on the internet is not going to see the IP addresses of your computers. It's just going to see the IP address of the router. And that's something the router does. It gives your network a public IP address that's viewable by the rest of the world. Finally, another role that is played by routers is acting as a gateway and firewall. So it's basically, in terms of a gateway, it basically allows for protocol conversions. So basically makes sure that even if your home network is using a different protocol than the internet or another network you're connecting to, that conversion is done so that they can communicate with each other. But also, oftentimes routers can act as firewalls, which allow you to kind of control what other computers and what devices can access your network and what can't, basically protecting you from unauthorized access and threats. So we've got an A-level function, or rather an A-level question. Describe the role and function of the router in the network. So these are basically the different functions: receive packets from the internet, find destinations of packets, forward packets, store, update, maintain a routing table, find the most efficient path. I think we've already seen basically all of these. Provides a local area network with a public IP address. For this question, you only need 3 from these, but generally knowing as many of these as possible is a good idea because it'll give you a broader understanding of routers, which are a very prominent topic on the A-level exam. Next, a school has a local area network. The LAN connects to the internet using a router. Describe the function of a router in a network. So again, it's basically all stuff we've seen before. There's one right here, network address translation. So that's something that might be worth knowing. NAT is a technique used by routers to allow multiple devices in a private local area network to share a single public IP address. So this is actually something we've seen before when I refer to a router basically having a single IP address. That's the only thing that's viewable to the world from your network. And that process or that aspect of a network is called network address translation. So basically the idea of a router having a single public IP address and all the computers within your local area network not being individually viewable to the outside world, but only accessible to that IP address. Next, Melinda connects her laptop to the internet through a router. Tick one box in each row to identify whether the task is performed by the router or not. So receives packets from devices, performed by router. Finds the IP address, no. Directs each packet to all devices attached to it, yeah. Stores the IP, yeah, that's it. Interesting. So I think we got all these right except for this one right here. Directs each packet, I guess this one is probably, this is probably a hub, right? So basically a hub is going to take data packets and send it to all the devices attached to it, versus a router would just send packets to whatever the intended destination is. So this is actually a question that integrates wireless access points and routers, which is actually one of the more common situations. A router has a wireless access point to allow devices to connect wirelessly. Identify 3 functions of the router and Andy's network. So again, it's actually pretty much the same thing, even though we are talking about a wireless access point. It's just The only difference the wireless access point makes is that it indicates that we can connect our devices to that router using a wireless network or wireless transmission. Now, the next device, well, this isn't really a device, but this is actually a protocol. And so the next concept we could say is also pretty well known and very important in understanding networks. This is Ethernet. So most of you have probably seen an Ethernet cord that looks like this. And the Ethernet cord by itself is not the device we're talking about. When we're talking about Ethernet, we're talking about a protocol for data transmission. And this is a protocol used for the transmission of data across wired or cable networks. It utilizes something called carrier sense multiple access / collision detection, which is basically a method to allow us to efficiently transmit data across cables. Data is transmitted in frames, and the idea of frames is similar to frames in, for example, a video, where, for example, a video is made up of multiple frames, and together they sequentially they make up the data that we want to communicate. Each frame includes a source and destination address, which could be an IP or MAC address, and each frame also contains some error checking method for resending frames that may have been damaged. And in a nutshell, that's what the Ethernet protocol encompasses. It's basically a way of sending data in the form of frames. It allows us to correctly and efficiently send data across a cable network. So this is an example of when we would use Ethernet. Basically, we have a bunch of devices that are using Ethernet cables to connect to a single, I think this is a switch probably. So one concept that we do need to understand is CDMA / CS, or carrier sense multiple access / collision detection, because this is the main protocol that's at work oftentimes when we're using Ethernet, but also more specifically in a bus topology network that makes use of Ethernet. And the reason we use this is to detect and prevent collisions. If you remember, on a bus topology network, whenever we send a signal, it's basically sent to every device. And so detecting and preventing collisions is actually really important. So firstly, before transmitting data, a device checks if the channel is busy. So is there any data currently being transmitted on that channel? If the channel is busy, the device waits. If it's free, the data is sent. Multiple devices can be connected to the same transmission medium. This is not really a step, but it's just an aspect really of a bus topology network. If there are two workstations transmitting simultaneously, this would cause a collision. And so this is a situation in which we wouldn't send data. If there is collision detection, then the transmission is aborted and a jamming signal is sent. And both devices wait for a random time before retrying. So each of those would individually send their own information, but they are going to wait before each of them tries to send that transmission again. And when they do, it's going to be they're going to be following these steps right here. So checking whether it's busy, and if it is, then waiting. If not, then just going ahead and sending the data. So really, I'd probably say 1, 2, 3, and 7 are the actual steps. Or actually, I guess 6 could be a possible step. 4 and 5 are just aspects of this particular protocol. Now we have an A-level question. Computers can be connected using Ethernet. Describe what is meant by Ethernet. And right here we have a few characteristics. So Ethernet, first of all, and most importantly, is a protocol. It's for data transmission through wired or cable network connections. It uses CSMA. Did I keep saying CDMA? I don't know why I said CDMA, but it's CSMA / CD. Data transmission is done in terms of frames, and we have different characteristics of frames. From these, you only really needed 3, so I guess just know 3 of these. Next, a local area network uses a bus topology. Describe how carrier sense multiple access / collision detection is used in a bus network. So you needed 4 points from this. So it's a protocol used to detect and prevent collisions. Before transmitting, a device checks if the channel is busy. If it is busy, the device waits, otherwise it sends something. So if 2 workstations can start to transmit at the same time, we get a collision. If a collision is detected, the transmission is aborted, a jamming signal is transmitted, and which basically prevents anything from transmitting. And then both devices wait for a random time to try again. So actually, like, the sort of steps or aspects I showed in the previous slide were taken from this mark scheme. I do that because, like, this is literally the information you need to know. And when I show you these questions, it's just kind of a review of what we already went over. Next, state three tasks performed by devices to deal with collisions when using carrier sense multiple access / collision detection protocol in a network. So monitoring the communications channel is one. Send data only when there is no data being transmitted. If we detect a collision, then we transmit a jamming signal. We wait for a random time if that happens. And if there are multiple collisions, we might increase random time. That is something I actually don't know what that means. What I imagine that means is that we might increase the amount of time we wait between sending signals in some random way. But either way, you just need to know three of these, and these are already aspects of the CSMA CD protocol that we saw before. Now, the last concept we're going to cover in this section is going to be bit streaming. And bit streaming is basically the idea of streaming data over the internet. And YouTube is a great example of it when we stream either video from YouTube servers, or even when we stream data in real time when someone is streaming from their own phone or something. But basically, bit streaming allows the real-time delivery of multimedia content. And again, it's used for streaming online media or live broadcasts. And the idea is we want a steady, uninterrupted flow because obviously it's not very convenient, or you don't want to watch a video that just keeps buffering all the time or just keeps stopping. And we receive data devices. So receiving devices buffer data to ensure smooth playback. So basically, when we do receive data, we're not going to receive data just second by second, right? So oftentimes we'll get more data than we need. So if we're watching a video, we might get the data for the rest of the video before we finished watching it. And this is a buffer. So we're going to store data ahead of time. And so then when we watch the video, we're watching it in real time. We're watching at the speed that's been intended. You don't really need to know these, but we do use specific protocols, like for example, HTTP live streaming to enable this. And the idea is we want to minimize latency. So we want an uninterrupted flow of information, so that, for example, we can watch a video in the speed that it was intended at, and it's not just like stopping, or it's not skipping ahead or doing anything weird. And that, that essentially is bit streaming. Okay, so our next section is going to cover the internet and the World Wide Web. Now, basically what the World Wide Web is it's the information on the internet. So all of those web pages that you see, which are really written in hypertext HTML, and multimedia content, that consists of the World Wide Web. So the World Wide Web are interconnected documents that you see on the internet, and these documents are connected by things like links. So HTML and URLs are a part of the World Wide Web in the sense that HTML allows us to create and structure web pages, and URLs allow us to identify and locate those web pages. And as I said before, we are able to access the World Wide Web through web browsers. So in a sense, if we're talking about the internet and the World Wide Web are two different things, but what you see in your web browser, those documents, those images, multimedia, all of that stuff, that is what the World Wide Web is. So this is just a diagram. Really, when we're talking about the World Wide Web, we're talking about that HTML component right there, and the URLs that allow us to access different HTML content. Now, the internet, on the other hand, is the physical infrastructure that enables the World Wide Web. So it's basically a vast interconnected system of computer networks that communicate using standard protocols. Some examples of standard protocols include things like TCP, IP, and also HTTP. Basically, the internet allows for the exchange of data and information through services like email, file transfer, and the World Wide Web. So the World Wide Web isn't the only thing on the internet. There are other services that are running on the internet. But the internet is the physical infrastructure that allows us to utilize and access the documents, the information, the multimedia that is the World Wide Web. And the kind of infrastructure we're talking about are things like routers, servers, cables, and the software that facilitates connectivity and communication. So a lot of the different protocols and network devices that we've been talking about in the previous sections are what allows the internet to be what it is. Now, if we're to compare the World Wide Web and the internet, probably the best comparison I could give is information versus infrastructure, with information being the World Wide Web and infrastructure being the internet. So we've kind of gone over these different distinctions. So the internet interconnected computer networks, World Wide Web, interlinked hypertext documents, and multimedia content. So really the content. The primary components of the internet are hardware, and the primary components of the World Wide Web are things like web pages, HTML, and URLs. Some of the most common protocols are TCP/IP on the internet, versus the World Wide Web is HTTP, HTTPS, HTML, stuff like that. I think I accidentally mentioned HTTP as being one of the protocols that runs on the internet, or maybe this wasn't an accident. I mean, it is technically a part of the World Wide Web, but it is going to be running on the internet. There's not really anywhere else that the World Wide Web runs. So I think the functions are pretty clear. For the internet, we're mainly exchanging data, and in the World Wide Web, this is more about presenting content. And the way we access the internet is through network interfaces and software, and basically by things like modems and basically like through the devices like routers that we would use to access the internet, really using more of those like hardware, more hardware to access the internet itself. So network devices, routers, cables, switches, just anything that enables us to create a network that we can then connect to the internet, or that allows for ISPs or internet service providers to work. Those are what we could consider to be access tools for the internet. Versus the World Wide Web, it's much simpler. We're just using web browsers like Chrome, Firefox, etc. Now let's take a look at an A-level question. Melinda sends emails from her webmail account, which is an email account accessed through a website. Explain whether Melinda is using the internet or the World Wide Web or both. So the answer here is that she's actually using both. She's using the internet because she's sending data on the infrastructure of the internet. She's using the World Wide Web because she's accessing a website. So really, she is using both. The next concept we're going to use are IP addresses. And IP addresses are, we've talked a little bit about this before, but they're basically the addresses of every server on a network, or in this case, the internet. So an IP address is a unique set of strings that's separated by periods or colons, and identifies each computer using the internet protocol to communicate over a network. So there are two versions, something called IPv4 and IPv6, and we'll talk about the distinctions between those later. But the IP address is basically an address for every computer that, if we're talking like, so computers and networks have their own IP addresses, like private IP addresses, but I think we should probably focus on the internet. And in that case, we can say the IP address is the address of every computer on the network, on the network that is the internet. So every computer on the internet, or every computer that's communicating on the internet has its own IP address. So we can use the IP address to specify the location of the device. So we basically use the IP address when we're trying to access a website or trying to access another server or some sort of device on the internet, because through the IP address we know where to send data to and where to receive data from. It basically allows us to communicate with specific devices on the internet. And without the concept of IP addresses, the internet doesn't really work, because we can't route packets between networks and between devices that are on the internet. It's kind of the same way as like without having physical addresses, we wouldn't be able to send mail or really send things to people anywhere. Now, one thing we do need to do is convert IP addresses to things called domains, or really not even domains, but I would say URLs is what we're going to be focusing on. Uniform resource locators. So this is the idea of as typing in google.com, and this being converted into an IP address, the actual IP address of google.com servers. We could actually just type in the IP address, but we oftentimes don't do that because it's a lot more convenient to type in google.com than type in an IP address that looks like this into a web browser, but both of them would work. So URLs, which we just kind of refer to, are the address you type into your browser. We don't necessarily need to know this, but it's just good to understand that every URL contains something called a protocol, which is this HTTPS business, a domain, www.something, a path, which is indicated by a slash, and then the actual web page that we want to access, which is indicated right here. Now, not all URLs may have a web page or a path, but they're all going to have a protocol and a domain. But this is a URL, and as we kind of indicated before, URLs are mainly used to be able to access websites more easily. And when we type in a URL, that's going to be converted into an IP address so that we can actually access whatever website we want to access or whatever web server or network on the internet that we want to access. Now, this conversion of a URL to an IP address is done through something called DNS, the domain name system. So we'll go through some of the steps here. Basically, when you type a URL into your web browser, it gets sent to a DNS server. And there are a fixed number of DNS servers that are located around the world. They're basically a part of the internet, and they're maintained by different organizations, but their utility is in converting URLs to IP addresses. They're basically like a phone book where there's just a bunch of URLs next to a bunch of IP addresses in a table. So the domain name server checks if a URL exists in its list of URLs, and if so, it returns the corresponding IP address to you, the user, to your web browser. And then your web browser can automatically send a request using this IP address so that we can access the website. So basically, you are typing in a URL, it gets sent to a DNS server. That DNS server returns the corresponding IP address to you, and your web browser uses that IP address to then access the website. But every domain name server has like a fixed list of URLs and corresponding IP addresses. So if the URL you want to access is not found in the first domain server, it passes the user request onto other DNS servers in the hierarchy until there's a match, at which point it sends you back the IP address. So there are a variety of DNS servers, there are a number of DNS servers out there that collectively hold all of the URLs that are on the internet. And if the first one doesn't contain the URL you want to access, or for the website you want to access, your request just keeps getting passed on to all the other DNS servers. Now, if you do need to access another DNS server, when your URL is found, the URL is sent back to the original DNS server. It's the first one you sent a request to, and then the user's web browser makes the request. Or actually, I would say the IP address, not the URL. The IP address that corresponds to the URL is sent back to the original DNS server, the first one you tried to access, and then your web browser can use that to access the website. So this is like a little diagram. So basically, you're at your web browser. You type in a URL, sectigostore.com. That gets sent to a DNS server, and then you get a response. And then your browser uses that IP address to then connect to sectigo.com servers, and then you get whatever HTML or whatever content is at that particular web server, or because delivered by that web server is at that website. Now, as we kind of said before, there is something called a DNS hierarchy. So DNS servers are a common resource for everyone on the internet, and they're regulated by a global non-governmental organization, the Internet Corporation for Assigned Names and Numbers, or ICANN. And I guess this is done in conjunction with other organizations like the Internet Engineering Task Force and the World Wide Web Consortium, W3C. So they're regulated and managed by these organizations, but they're operated by ISPs or internet service providers and domain name registrars, of which an example is GoDaddy. So yeah, I just want to make that distinction. I may not have said that correctly before, but regulation is done by non-governmental organizations. Actually, like operating and maintaining these physical DNS servers is done by internet service providers and domain name registrars. And there's no fixed number of DNS servers, but it's pretty large because anytime someone types in a URL, it needs to be sent to a DNS server to then be converted into an IP address. So this is just to clarify like what DNS servers are and how they're managed. In previous slides, I may have just kind of not referred to that specifically, but here's that information. Okay, so now that we've actually kind of touched on the concept of IP addresses, we're going to dive into this with more depth. So the first thing we're going to talk about is what like IPv4 and IPv6 actually are. Because we know that IP addresses are used to basically allow us to connect to different computers on the internet, but there are actually two types of IP addresses. The first being IP version 4 and IP version 6. So basically IP version 6 was created because there were too many devices on the internet to simply be able to address with IP version 4. So IP version 4 is basically 32 bits long, and it's basically 32 bits long, and each one of these 4 groupings of numbers collectively represent that 32 bits. So 4 bits each, right? So basically a combination of 4 4-bit values. And this gives us 4.3 billion unique addresses. But like once people started connecting refrigerators to the internet, it was pretty obvious we needed more than that. So IPv6 or version 6 came into existence. This has a 120-bit address length, and it looks something like this. So basically we basically have eight groups of 16 bits. Now, so basically IPv6 is newer, but it's also more secure, and it just incorporates better security practices by default. It has support for something called IPsec. And I mean, in using IP version 6, we're also using a slightly different protocol, which brings with it a more modern, secure approach to addressing devices on the internet. So again, like to kind of summarize, with IPv4, we have a 32-bit address that looks like this, with 4.3 billion possible addresses. IPv6 is going to look something like this, and it's going to be 128 bits, and it's going to have 340 undecillion possible addresses, which is probably enough, but that is the main difference between these. So right here we have an A-level question, and it basically asks us to fill in the blanks for some of the characteristics of IPv4. And I guess the beginning of the question is the CCTV cameras are connected to a network and transfer their data wirelessly to a central computer. And this involves IP addresses, so we need to sort of address some of the basics of IP addresses. So an IPv4 address contains 4 groups of digits. Each group is represented in 8 bits. And the groups are separated by full stops. And for those of you who are not from the UK, a full stop is just a period. So 192, so for example, 192 point, this is a full stop, and so forth. Now an IPv6 address contains 8 groups of digits. Each group is represented by 16 bits. Multiple groups that only contain zeros can be represented with a, I guess, double colon. So if you go back to our example right here, we had 2002 colon db8, and then we had a double colon, which means everything in there is going to be a 0. So it basically the equivalent of like this. But anyways, that is what you need to know about IPv4 versus IPv6. We have some other questions though that are involving IPv6 and IPv4. A local area network contains 4 devices, a router, 2 laptop computers, and a server. A server has the IP address 192.168.3.2. Explain why this is not an IPv6 address. It's kind of a weird question. I mean, it's just not. Like, first of all, it doesn't have enough groups. It uses full stops or periods and not colons. The values themselves, each of these groups don't represent 16 bits. So there are a variety of reasons why it would not be IPv6. And I think those are pretty much highlighted here. Notation, number of groups, overall bits of data that are represented by the address. Those are all distinctions. Now, the next concept we're going to talk about is probably honestly one of the more complicated concepts, and it's called subnetting. And it's basically a method by which we would divide a single network into multiple smaller, more manageable networks. And we kind of do that by creating, so within a network, creating a range of IP addresses that corresponds to each subnet or each smaller part of the network. So there is actually a slightly mathematical process to this that we need to know. And basically, in order to go from just a regular network address to a subnet, to a network that employs subnets, first we need the original network IP address, and that's this one. This 24 is basically the length, or how many bits are indicated in our subnet mask. And this is a subnet mask. So just to start out, we need our original network IP address, which is right here. And we need our subnet mask, which is right here. And our subnet mask looks like an IP address, but it's really something that we combine with our original network IP address to get the address ranges of our subnet. And this 24 right here is basically the number of bits of our subnet mask. So basically, right here, remember in a regular IP address, we have about 32 bits. And right here we have 255, 255, 255, and 0. So this is really just 24 bits. And sometimes, depending on what we need, we might have a subnet mask that looks like this. .0.0.0, which is just going to be 8 bits. So that's what this /24 represents. Now, basically what we need, okay, our network IP, a subnet mask, and then the number of subnets. We need to know the number of subnets that we want to make, so the number of different sections of our network we want to make. An example might just be 8 subnets. And then, so based on like the number of subnets we have, then we might need to create a new subnet mask, and that might look something like this. And again, this is going to be based on the fact that we want to divide we need to divide our network into 8 separate components. So we're going to have network IP, original subnet mask, and then we're going to create a new subnet mask based on the number of subnets that we need. Now let's take a closer look at this process with some depth. You don't actually need to know all of this, but things kind of make a bit more sense later if you have just an understanding of how this whole process of going from an IP address to subnet IP addresses sort of works. So let's say we start with a network IP address of 192.168.1.0, and that's going to be 24 bits because we have a 0 at the end. Now, let's say we want 4 subnets. So we're going to start with our original subnet mask, which is going to be right here. And to get 4 subnets, we basically need to add 2 bits to this original subnet mask, with the idea being that 2 to the power of 2 equals 4. And so that's going to give us 4 distinct ranges in terms of our subnets. So it's going to give us 4 distinct ranges that allow us to allocate space to our subnets. Now, what we're going to do is we're going to add 4 in binary to this value in binary, and we're going to end up with something like this using binary addition. Like, you don't need to know how to do that. I'm just trying to illustrate how we end up with a new subnet mask, which is this. And then based on this new subnet mask, we can then allocate ranges for different subnets on our network. So we can say that from 192.168.10 to 64, that so basically from 0 to 63, those are all going to be subnet 1. 64 to 127 would be subnet 2. 128 to 191 would be subnet 3, and 192 to 155 would be our subnet, or 255 would be our subnet 4. And those are all the ranges in which would correspond to our different subnets. Now, I'm not going to go into this because now when we do work with our IP addresses, one thing we do need to know is the distinction between network IDs and host IDs. And these host IDs are really what we're changing in order to be able to allocate. So these are going to be our ranges for our subnets, right? And their network ID is going to be basically everything else. So if you go right back here, this was basically our network ID, and this was our host ID. Just like another kind of note on subnet masks, we have different classes. So this right here is going to be an 8-bit subnet mask because we only have 255 right here. This is going to be a 16-bit, and this is going to be a 24-bit. And yeah, I mean, whether we work with any of these is going to be specified in the question that we're dealing with. And the big distinction right here is that if we do only have an 8-bit subnet mask, that means all of these can function as hosts. These can all give us different combinations for it. Together, they can give us different combinations for a subnet. And so with a 8-bit subnet mask, we can have 16,777,216 hosts. Less so with a 16-bit subnet mask, and the least with an 8-bit or a 24-bit submask rather. So this is our host. These are our host IDs right here, and the rest is going to be our network ID in our subnet mask. So that being said, let's go ahead and take a look at it at a level question. So a subnet mask is used when subnetting a LAN. 2 devices in the LAN are located in different subnetworks. The IP addresses and corresponding subnet masks are shown right here. So for the first IP address, so we have an IP address right here, and we have a subnet mask right here. And this IP address is going to be something that's already been calculated. So you've gone through the whole process of calculating our subnet IP addresses using our subnet mask. So right here it says identify the following network ID and host ID. So the network ID for the device with IP address 10.10.12.1 So because our subnet mask is actually going to be pretty big, it's going to be all of this. That means that our network ID is just going to be this right here, and so our network ID is going to be 10. Now the next question, the host ID for the device with IP address 192.168.12.4, is this right here. Now our subnet mask is actually quite small, which means that in the end, this is going to be our network ID, and this is going to be our subnet mask, or this is going to be our host ID right here. So our host ID is just going to be 4. And obviously we're right. Now, why do we do subnetting? There are some advantages to subnetting. The first is LAN security, because basically when we use subnetting, that means that it's actually kind of a virtual local area network system. When we use subnetting, what we're actually doing is we're basically dividing our network into multiple components, and we can grant access to users who are coming in to specific subnets or specific ranges of IP addresses. So basically, they would view a subnet as a different network in a sense. So that means that they're only going to have access to a certain range or a certain part of our network, which means that if they do something wrong, or they do something that damages our security, or is basically something that is that's not what we want, then that sort of infiltration or problem is only isolated in that subnet. Moreover, kind of going in line with that concept, it allows us to more easily manage a network. Because of the fact that this is basically dividing our network into multiple components, if something goes wrong, it makes it easier to isolate where that happened, right? Because if something goes wrong, we can say, okay, it happened in this IP address, which is in this part of our network, hence these computers in this smaller component of our network must be responsible for whatever happened. It facilitates network expansion. So basically, kind of using subnetting within our own network, we can allow for a greater range of IP addresses. We can basically divide our network into components, and then we have a greater range than if we're just allocating a fixed number of IP addresses without subnetting within our network. And finally, we can boost network performance using subnetting. Organizing our network into subnets allows us to localize communication within those subnets and reduces congestion overall, because particularly if we're dividing our network into different subnets for example, different departments, most of the communication can stay within that department and hence within that subnet. So we don't need communication going between different parts of our network where they're just not going to be needed. The thing is, if we didn't have subnets, then any messages we're sending, they might traverse other parts of the network that are not relevant to them, which is okay except for the fact that it increases network traffic and overall increases the load. Versus if you can keep them within a subnet, and there's no unnecessary messages going between different parts of the network to which they're not relevant. And now we've got an A-level question. Subnetting can be used to separate a network into logical segments. Describe 2 of the reasons why subnetting is used in a network. So, improve the security of our local area network. Network management is easy, more scalable, improve network performance, reduce network congestion. Local area networks can be made up of several subnetworks. Give 2 benefits dividing a network into subnetworks by subnetting the LAN. Again, improves security, reduces congestion, allows extension of network, aids day-to-day performance management, improves performance. Network makes use of subnetting. Describe 2 benefits of subnetting a network. And this is just more of the same. And finally, one site has split the network into several subnetworks. An IP address in a subnetwork is divided into 2 parts. Identify and describe the 2 parts of an IP address in a subnetwork. And this is actually interesting. This refers to the network ID and host ID, which we talked to before. So each device in a subnetwork has the same network ID, right? And each subnetwork has a different network ID. So every device in each subnetwork has a different host ID, but the same network ID, and the host ID uniquely identifies the device within the subnetwork. So this is actually a little bit weird. I would actually say that, I guess it kind of depends on how the subnetting is done. But in a lot of cases, the network ID can stay the same, and the host is really what's going to change, because remember we had that range of hosts for each subnetwork. So this one is actually a little weird, but this one makes complete sense. I mean, the host ID is going to be different for every single device within a subnetwork, and the network ID is going to be, I mean, every device in a subnetwork is going to have the same network ID. Like, that's not going to change. Now, the next concept we're going to address is going to be IP address assignment. So how we actually assign addresses to to different devices. And this is something that comes up often when we're talking about routers and local area networks, because they are responsible for assigning IP addresses. So right here, I'm actually going to change this heading right here. So this should be dynamic, and this should be static right here. But basically, dynamic IP addresses are used in the context, again, of routers. And IP addresses are automatically assigned and rotated by something called a DHCP server, which is something that's located inside a router. And generally, addresses will change with each connection to a router. So every time you connect your laptop to a router, you're going to have a different IP address on that network. And overall, there's a reduced security risk, because if your IP address is changing each time, and if someone's attacking a network, they're not going to really know they're not going to be able to target your IP address specifically. Also, IP addresses in general are going to be changing, so this kind of makes you more of a moving target on a network. Now, static IP addresses are fixed IP addresses manually assigned, and they remain constant unless they're changed manually. So they're basically fixed. This is going to be the IP address of your router, and this can lead to higher risk because of the fact that your IP address doesn't change, so it's a more consistent target to be attacked. Mainly, dynamic address changes every time you connect to a network. Static address is going to change the same. Typically will correspond to something like a router that allows you to connect to the internet. And the next concept we have are public and private IP addresses. Now, public IP addresses are those addresses that, again, your router might have that can be accessed by anyone on the internet. They are unique. They identify unique devices globally, and they tend to be more exposed to external threats like security threats, because anyone on the internet can access a public IP address. Now, private networks are those that are not accessible directly from the internet. They are within your network, and they are those addresses that may be assigned just by your router. So they allow for internal network devices to communicate with each other, but not necessarily to communicate with the global address space. So if you had a private IP address and you're inside a network, then you'd have to go through a router which has a public IP address to communicate with the rest of the world. And again, they're more secure because these private IP addresses are not directly reachable from the internet. So now we've got an A-level question here. So the following table contains types of IP addresses and their descriptions. Complete the table by writing the missing types of IP addresses and the missing descriptions. And this is basically a rehash of what we just said. One thing to keep in mind, static IP addresses don't change each time a device joins a local area network. Dynamic IP addresses change each time a device joins a network. Everything else is pretty much the same. Private IP addresses are mainly used for internal LAN communication. And public IP addresses are allow direct access to the internet or are assigned to a device. Basically allow that device to interact directly with the internet. Okay, so now our last section is on random hardware. These are just like random devices or random systems that are somehow part of this topic and are somehow tangentially connected to the internet or communications in general. So let's get started. First is a modem. You may or may not have seen these. These are basically something we use to connect to the internet. And in a lot of cases nowadays, these modems are combined with routers and wireless access points. So basically they convert digital data into analog signals for transmission over communication lines and vice versa. And if you're using a modem in your home, you're probably getting an analog signal, probably from like your cable outlet, and that's being converted into digital data, which can then be used for you to access the internet. So basically, these are used to enable internet connectivity by linking your local network to an internet service provider. There are other types of modems like dial-up modems, DSL, cable, fiber optic. Most probably you're using a cable or fiber optic modem to be able to connect your local area network to the internet. Also, oftentimes modems contain, as we said, integrated routers, firewalls, Wi-Fi access points, and possibly VoIP support, voice over IP. And the next is a publicly switched telephone network, which is just like, it's how telephone used to work in the old days, I guess. And basically there's a switchboard, and it's actually not that different from like a network switch, to be honest, but you make a phone call, your phone call goes through to a switchboard, and that routes you to someone else's phone number. And this used to be done physically before. Now we have digital switchboards that enable this for anyone who still uses the phone. So basically a circuit switch network for telephone communications, allows for voice communications and data transmission. Basically uses analog signal transmission, but nowadays, so it'll use digital signaling for setting up and disconnecting calls. So to actually kind of like start the call and allow you to connect, that's all done digitally. And also when you hang up, but the actual voice transmission itself may be analog. And the infrastructure usually composed of telephone lines, fiber optic cable, possibly microwave transmission links, satellites, undersea telephone communications, and or cellular networks. But in general, I think we're kind of talking, like probably most questions are just going to involve something like this. The next concept is dedicated lines. And these are basically lines, could be fiber optic, could be copper, that are dedicated to a specific purpose, usually for more high volume communications. So these are exclusive communication pathways reserved for specific data, voice, or video traffic. And there are different types of lease lines. So one is just a leased line, like a line that someone pays for. You might have heard of a T1 line before. That's it's largely used for internet, for businesses. And ISDN is kind of an older concept. I mainly heard of it used in the context of making voice calls, but it allows you to simultaneously transmit voice, video, and data. These I may have seen ISDN before. I don't think you need to know what these are, but these are just examples. And the main benefits are high uptime, because these lines are simply dedicated to your business or to your particular use case. Predictable performance without fluctuation, because no one else is using these lines except for you and your coworkers. And enhanced security, again, because you're not sharing the line with other people, so they don't really have any way to access your data. And again, these are usually used for businesses for secure, high-speed internet access, data transfer, and VoIP. And I'd probably say things like data centers are another, obviously these are businesses, but these are another main use case for dedicated lines. These do tend to be more expensive than shared connections because all the infrastructure is literally dedicated to just your organization. And finally, we have cell phone networks. Basically, you communicate with a mobile tower. That mobile tower may send you to another piece of infrastructure, and that piece of infrastructure might pass you over to the mobile tower closest to whoever you're talking to. They're wireless communication systems. They involve a cell tower, base station, and potentially a mobile switching center, which is that center that basically sends your whatever you're saying or your data onto the relevant cell tower near whoever it is you want to communicate with. Basically uses technology like GSM and CDMA, or LTE and 5G in the case of using the internet or mobile internet. And again, the infrastructure is interconnected cell sites equipped with transmitters and receivers to cover areas. And I guess we talked about the mobile switching center as being the main piece of infrastructure between cell towers. But also if you're connecting to the internet, there's probably going to be some other internet-enabled infrastructure. But also there are things like base stations, which play another role in managing traffic. You don't necessarily need to know these components, but this just gives you an overall summary of what cell phone networks are. I will say that I haven't actually seen any questions on cell phone networks or any of these random hardware devices or hardware systems, but they're on the syllabus, so I just thought I'd cover them. Now that brings us to the end of this video. I'd like to finish out with some channel updates. So at the moment, I am working my way through the paper 1 topics, but I'm going to take a little break to work on a paper 2 course. It's mainly going to focus on programming for paper 2. And then I'm also working on a paper 3 study guide, and probably after that I'll continue with paper 1. So paper 1 is still something that's in progress, but these two are kind of my priorities right now. Anyways, if you found value in this video and you want to see more like it, please like the video and subscribe to the channel. Have a nice day and good luck.